Okay, thank you, Brian, for the introduction. My name is Yu Feng. I'm a CEO of Veridice. I'm also a CS professor at UCSB, working on formal verification and program synthesis. And Junrui is my PhD student, and today we'll be talking about some of our ongoing work on applying formal methods to ZK circuits. So here is a quick roadmap of today's talk. So at the very beginning, I'm going to give a brief introduction about some terminology about formal method for those of you who might not familiar before, so that we are on the same page. And then after that, Junrui is going to give you a brief introduction about the formal verifications for core Circom library that he has been working on. And I'm going to wrap up the talk with another tool, which is essentially completely push button, that will allow you to reason about some common vulnerabilities in ZK circuits. And at the end, so I'm going to briefly talk about some ongoing directions about our current toolings. Okay, so you might heard of the term formal verifications and formal method interchangeably, but what are they exactly? So when we talk about formal method, so it's not referring to a particular technique or a particular tooling. It's actually a set of method that will allow you to essentially mathematically reason about the behavior of a program with respect to some property that you care about. For instance, going from the left of the bottom to the right corners of the figures. So essentially, as you can see, you can do testing, which is essentially purely push button, and then so it doesn't involve any human. So you just need to provide the software. But the problem is that the guarantee that you're going to gain from testing is going to be very low. For instance, the fact that you cannot find any bug by doing fuzzing doesn't mean that your software is actually safe. And on the other extreme, you can actually do formal verification, which essentially someone needs to sit down and then provide the correct behavior of piece of software such that the tool can actually prove the actual implementation of your code base actually conform with the specification. However, despite that, it gives you the highest guarantee, so it requires a tons of manual effort to make the proof proceed. So that's why we also have a bunch of variants in the middle. For instance, one of the variants is essentially bounding model checking. So this is essentially the toolbox or tooling we have. So, but what's the problem we are trying to address, right? So in order to understand the problem, so we need to look at the architecture of a typical application that use ZK. So in the sense that when we talk about ZK, they are not just like independent of piece of software. They typically embedded in a piece of applications. For instance, in this case, it's going to be a smart contract on blockchain. So which means that at the very bottom, there will be some core ZK library that is going to be shared by all the application circuits that are built by different kind of vendors from the industry. And then at the top, so those circuits is going to interact with the smart contract. So which means that, so the architecture is actually very similar to like a standard software system that we have seen over and over again in Android or Linux kernel. And as you can see, this because of the system is so sophisticated, and there's not a single approach that can cure all of the problem in this stack. So that comes to the tooling I'm going to describe later. And then so you might wondering, so what's the problem of this architecture, right? What's the problem? So we all know that so those software, no matter they are ZK or operating system, they all have bugs because they are written by humans. For instance, before we even start this project, we actually do a very sophisticated study on those GitHub from mainstream teams such as ADO as well as Polygon Hermes to try to understand, analyze their GitHub history, and then especially on those issues about their bug list. And then this is just a snapshot of the issue list that we collect from the SNUG VM from the ADO team. As you can see, those are essentially the bug they identified in their development phase for the SNUG VM. It includes a variety of different issues, including like a missing range check that potentially could compromise your circuits, as well as non-deterministic proof, in a sense that while the ZK circuit can give you non-deterministic answer, given a particular different input, okay? So which means that we know the architecture, and then we also know the problem, and how are we going to deal with that? So the way we attach this problem at Veridice is essentially, we don't believe that there's any single tooling or technique can solve all the problems. So what we do essentially, we use a hybrid approach. in a sense that at the bottom of the software stack, including those common libraries that are being used by all the vendor from the industry, that's the place that you don't want any compromise. Okay, so to address this problem, we actually developed a Coda, which is essentially an interactive theorem proof tooling for formally verified ZK circuit. In particular, so we instantiate the idea into Circom, but our approach is actually agnostic to the programming languages. So this is pretty manual involved because it requires a lot of domain expert knowledges. But the good thing is that you only need to deal with this library for once. Okay, so which means that ideally, once you formally verify those libraries, you can actually plug in the result on top of those libraries such that the developer can just reuse those kind of proof and then start to build their application circuit. And once they build their application circuit, because those circuits are typically very large, and then we also develop a PyCast framework, which essentially allowed the developer could essentially finding bug in a push-button manner. Okay, in this case, so the developer just need to provide a property. In this case, is in, let's say, first-order logic. And then PyCast was able to automatically finding vulnerabilities in your application circuit. Okay, so now I'm going to switch gear and let Junrui to introduce the first framework that he has been working on about applying formal verification to verify the functional correctness of coarse ZK circuit library.
Yeah, so is it working?
Yeah.
Okay. So before I jump into our framework, let me just give you a little bit of motivation of why programming circuits is so hard. So if you have previous experience programming, let's say like in Circom, you may have noticed that it's quite different from the usual programming, right? If you're using Python or something, you have a lot of tools to make it easy to express a piece of computation. For example, you have variables, mutations, loops and conditionals, and functions and OOP, and all this good stuff, right? But if you're using Circom, all you have is quadratic equations over signals, which are taken from a finite field, and some syntactic sugar. Right. So if you have not programmed in Circom before, let me just show you a very simple example. So suppose you want to express the computation is 0, which is a function that returns 1 if the input is 0, and otherwise the function returns 0, right? If you're using Python, you can see on the left that you can just use a simple if-then-else statement. But if you use Circom, you have to come up with two very clever equations that constrain the input x and output y, and also a magical signal inf, right? So it's not immediately clear why the Circom circuit is doing what we claim it to be doing, right? So to ensure that the circuit is doing the right thing, one thing you can do is to write an informal proof to convince yourself or others that use your circuits that the circuit is doing the right thing. And however, the problem is that, so the informal proofs are mostly for communication between humans. First of all, it takes a human to understand your proof and being convinced that your proof is correct. And second, you may have some errors in your proofs, right? So it would be great if we can have some machine to, so that after we write down the proof, the machine can check our proof for us. And this is what the proof assistants are for. So basically using proof assistants, such as the Coq proof assistant, you write down the program called the proof script that generates the proof, and the proof system checks that your proof actually proves the things that you claim to be proving. So let me show you a very simple example of this is 0 circuit. So what we do first is that we take the Circom circuit and we translate that circuit into Coq's language. You can see that this is a very straightforward translation. Each equation corresponds to one conjunct in the conjunction you see at the very top. So translate a circuit, and also we write down the formal specification of the is0, which is a very simple mathematical function. Right? And then we state the soundness theorem, which says that for all the signals in the circuit, if they satisfy the constraints of the circuits, then they actually conform to the specification. And in Coq, what you do is that you write down a program called a proof script that incrementally builds a proof such that the proof actually proved the things on the right-hand side. And you can see that as we step through this program, the proof system keeps tracks of what you need to prove in the next step. And once you finish the whole thing and you write the QED symbol, the clock is going to check that your proof is correct. So let me skip to the next slide. So using very similar techniques, we developed this framework called Coda for certifying ZK circuits. And right now we're mostly focusing on Circom. And some of the libraries that we have already certified include the big integer library. We have certified more than 80% of it. And the big integer library is used by Circom ECDSA, Circom pairing, etc. And also in the process, we also certify like a number of Circom lift circuits, like comparators, bitified gates, and so on. So if you happen to use those circuits in your project, you can be pretty sure that those circuits are not doing the wrong thing. So let me just recap the Coda workflow. If you have a piece of circuit that you want to make sure that is correct, as a developer, you first encode your circuit into COC and write down specification, and then you construct a program that proves the soundness of the circuit. But suppose you just want to make sure that some circuits developed by others is correct. As an auditor, all you need to do is run the proof script and make sure that COC doesn't complain. So you don't need to read the informal proof and try to understand it. All you need to do is just run a simple program. So this gives us a very simple way to obtain the highest assurance about the correctness of the circuit. And I think I'll just briefly go through some of the challenges that we encounter while proving, for instance, the big integer library. The first challenge, of course, if you have done any manual proving using proof assistant before, that is the challenge is proof automation. Like, it's very tedious to write those kind of manual proofs. So what people do is that they develop specialized decision procedures or tactics that automatically construct those kind of proofs for very specific goals. The second challenge is that if you program in Circom before, you may have noticed that it's a very low-level language. Well, the good thing is that you can do a lot of optimizations, but the bad thing is that it's kind of tedious to write down all those, express your computation using this low-level language, and also makes it difficult to verify, because whenever you have a circuit with all those nested for loops, in order to prove that this circuit is correct, we as the verifier has to provide what's called the loop invariance to every loop that you see here, and this is often a very tedious process. So what we do is that we're designing a relatively high-level domain-specific language for describing the behavior of circuits to make it easier to both write down the circuit and also to make it easier to prove that circuit is correct. And the third challenge we encounter, especially during the proof of the big integer library, is range checks. So recall that the Circom signals are taken from the finite field. So whenever you perform field addition or field multiplication, those operations might overflow. And what we found is that about a third of our proof is dedicated to range checks. So if we can find a way to simplify those proof about range checks, it would be great. And also, if you're a circuit developer, there has been known circuit bugs that is caused by the missing range checks. So if we can somehow automate the proof about range checks, maybe the same technique can be used to infer the best range checks automatically for you. Yep. So this concludes my part about formally certifying the library circuits. And here's the GitHub repo. You're welcome to audit our circuit and spec encoding. And also, if you have some circuits that you wish to verify, you can contribute to proofs yourselves. So with that, I'll hand it back to you.
Okay, thank you. So why the previous Coda framework can give you the highest strong assurance regarding the behavior of a circuit, you might obviously observe a pitfall in the sense that you have to essentially sit there and then manually write down the COC proof to essentially accomplish everything, which is probably undesirable if you have a large circuit and then So in order to address that problem, we also have the second tooling, which is called Pegas. And what the tooling is essentially very similar to standard, like a common push-button verification that you have seen for smart contract, in the sense that it's a symbolic compiler. It's a symbolic compiler that takes two inputs. One is your program, and the second is the property that you want to verify. And then what it does is essentially it's going to automatically compile into constraint, which can be answered by off-the-shelf solver. So you might wonder, so what's the difference from the previous one, right? The biggest difference is on the property that you can specify. Since right now we care more about automation, so which means that here the property that you can automatically verify is going to be very, very restricted, in the sense that we can probably only answer like first order logics in terms of your variable. And also, so you might wonder why existing vendor or researcher, they cannot just automatically translate this problem into an off-the-shelf solver like Z3, because the problem is on the constraint side, in the sense that when you deal with ZK circuit, normally they can translate a lot of constraint that can easily choke your existing constraint solver. So which means that the approach that we deal with, essentially, we substitute let's say the mainstream constraint from Z3 with a finite field solver. And in this case, this finite field solver is actually come from Alex at Stanford. And essentially, you can think of it's a specialized solver that can understand finite field theory. And then the solver essentially to give you a solution about the property that you want to query. And so you might wonder, so is this that simple, in a sense that all you need is just to like swap the solver and then everything else is just going to be cured automatically? That's not the case, because when we like switch to the specialized solver, we can probably only handle, I think, 40% of the original benchmark that Acne can handle. And in order to bypass the challenges, on top of the existing finite field solver, we also develop our own decision procedure. And I'm going to walk through the high-level idea very quickly, since I'm running out of time. So in here, the property that we care about like can be anything that you want to reason about in your ZK circuits. And then our approach is actually agnostic to the property that you want to check. In here, one of the property that we inherit from 0xPower is the uniqueness property. In the sense that, let's say you have a piece of program on the right-hand side, and then when you translate into R1CS, it's a list of polynomial equations that constrain the scope of each variable. And then right now, what you want to enforce is that you want this output is going to be unique with respect to the input that you're going to provide it. Okay? And then, in addition to uniqueness, you can also like verify other properties such as equivalence between circuits. And what we are doing here is actually a customized decision procedure. And I'm just going to give you the high-level idea, because the actual algorithm contains like 4 or 5 pages. So what we do, essentially, you can think of it as kind of like a DPL style, but customized for ZK. So what we are doing here, you can think of at the very beginning, we initialize the knowledge. This K, essentially, you can think of it as a knowledge K. Okay? And what this knowledge is going to do is that you initialize the knowledge with the I. Okay? Where this I is going to be the signal from your input. And then, so what you want to prove is that you want to prove whether your current set of signal is going to be obeyed with respect to a property sigma that you pass at the very beginning of these functions. So what you're going to do is essentially, you're going to copy all those input signal to this propagation set P. Sorry, I cannot use the pointer. So a propagation set P, and what you're going to do is that you're going to jump into the loop. And then at the very beginning, so you're going to do propagations. Like what the propagation does is very similar to BCP process in traditional SAS solver, in the sense that based on the existing fact that you know about, you try to propagate as many facts as you could. For instance, if I know that I1 is going to be unique, and then I assign I1 to I2, obviously I2 should also be unique. You do this kind of propagation until you reach to a fixed point that you cannot do anymore. So after that, so that's essentially, you get stuck, right? At this moment, you get stuck. And then when you get stuck, what you want to do is that you want to pick some variable whose fact you don't know. And that's essentially this select satisfy signal is doing, in a sense that we apply a bunch of heuristic to resolve when you get stuck, what would be the best variable that you should be continue, okay? So you can think of this iterative loop keep going until you resolve all the signals in your current work list, in a sense that all the signals are already being done by by the solver, and then everything is actually conformed to be obeyed with the sigma that you provided. So in this case, you are going to return true, in the sense that the original signal is actually equal to the knowledge that you know, so you are done. Otherwise, which means that you fail to prove the property of those signal with respect to sigma, then you have to return false. And then, so in the between, so if you haven't finished that, which means that if the signal that you just checked is actually known to be true, meaning that it actually satisfied the sigma that you want to prove, and then that's where you want to keep going with the propagation. You can think of it as kind of a work list style that allow you to iteratively refine until none of the signals on your data set are known to be violate the property of signal. Okay, and then here's the part of the result. So as you can see on the Circom library, which is essentially a benchmark from the Acne project. So in terms of accuracy, we are actually almost close to 100%, compared to Acne that can only handle 74% of the benchmark. And then we also have a lot of ongoing results that we systematically evaluate on industrial like circuits, such as circuits from Polygon, Hermes, etc. And then as you go from left to right, sorry, we haven't put all the results there. And then you can imagine that the gap is going to be larger and larger. And what's more interesting is that during running our evaluation on the Circom library, we actually find 1 0-day bugs that are not reported before. Okay, so this is essentially everything that we want to present. And then regarding the next step, what we plan to do, essentially, we plan to finish the verifications on the library that use a big integer, including EC DSA as well as Circom pairing, etc. And we also want to extend our current pipeline that is go beyond R1CS, such as those constraint systems generated by Halo 2 and Pumpkin. And we are also working on a modular incremental solver that will allow the tool to reason about large circuits. For instance, right now, one of our clients, has a circuit that involves millions of constraints. So which means that if you directly throw those constraints into the solver, it's going to choke. So that's basically all we want to present, and thank you for listening. And then I highly encourage you to go ahead and access our tool and then provide feedback. Thank you so much, and happy to take questions.
So if the proof fails, how do you guys point out the missing constraints or the additional things that need to be added? Because I imagine the proof automation probably doesn't output a very clear this is missing.
If you give you a counterexample, for instance, when you ask a constraint solver, to check the uniqueness, right? When it say that this cannot be verified, so it's going to provide a counterexample. And sometimes the counterexample is intuitive enough to you. For us, essentially to point out not the direct constraint, because that requires some additional synthesis, but it can actually point out some relevant variable that you are supposed to be constrained, but you didn't.
One question. Oh, wait, did someone?
There's a question from.
Yeah, feel free to go up to the mic over here.
Yeah, so I was wondering if you guys had looked at some automation techniques for generalizing the proofs. I know there's some stuff in homotopy type theory where you can kind of transfer proof techniques. So if you guys had,
that's a very good point. So that's why I mentioned that and our next step on the first project is essentially the first thing we're trying to build is essentially we're trying to build a tactile library that essentially you can think of specialized for ZK in the sense that next time when you do the similar proof, you don't have to reconstruct everything from scratch. That's one automation that we have done. The second automation is that there is some additional manual effort need to be done, in the sense that during the proof you have to manually infer some lemma. some missing lemma that will allow the proof to proceed. What we are doing right now, essentially, we are exploring a reinforcement learning approach in the sense that you can think of, you let the prover to interact with the machine, and then the machine and then the prover when it gets stuck, it try to enumerate like a candidate, like a lemma that can potentially be true. And then every time, of course, a lot of attempts will just fail. But when it actually learns the lemma, that actually allow the proof to proceed. So you can think of the prover is going to try to generalize this kind of knowledge so that it can be reused by like a further like proof attempt. Any questions?
One more question that I have around the performance of ECNI versus PICAS on Circom lib is, if I recall correctly, some Circom lib circuits require preconditions where you need to assume that an input point is like on a certain elliptic curve or something like that. How are you taking account for that when you are running PICAS on those circuits?
Yeah. So that's actually contribute part of the delta that you see, in the sense that if you see the delta in which the case that we win. So one of the reasons is actually because of the precondition that you mentioned, in the sense that when we try to prove a circuit with respect to a property, when we cannot prove because of missing precondition, what we do essentially, we also try to do some kind of invariant inference, in the sense that you try to redefine a DSL that's like can use to express common preconditions in ZK circuit, and then when it cannot proceed, we will do enumerations. We will do enumeration and try to enumerate possible precondition that will allow the proof to be proceed. Yeah.
Cool. Okay, thank you so much.
Thank you.